In 1970, a Chevrolet engineer filed a technical report recommending that the LS7 454 not be approved for production. His reasoning? The engine produced torque levels that exceeded the design specifications of every transmission in GM's inventory. At Chrysler, test drivers were refusing to run full-throttle pulls in 426 Hemi prototypes after a connecting rod punched through a cylinder wall at 6,000 RPM. At Ford, the Boss 429 required special oil system modifications before it could complete durability testing without bearing failure. This is the story of 7 American big blocks that pushed engineering limits so far, even their creators questioned whether they should exist. Oldsmobile's 455 cubic inch engine in Stage 1 trim made 370 horsepower, respectable but not exceptional for the era. What worried engineers wasn't peak horsepower. It was what happened at 2,800 RPM. At that engine speed, the Stage 1 produced 500 pound-feet of torque. More concerning was how long it held that torque. The engine maintained over 470 pound-feet from 2,000 RPM all the way to 4,000 RPM. This wasn't a peaky race engine delivering power in a narrow band. This was relentless, constant force that subjected every component in the drivetrain to loads they weren't originally designed to handle. The technical problem was straightforward but serious. Every time a driver accelerated from a stop sign or merged onto a highway, the transmission, drive shaft, and rear axle experienced shock loads at the upper limits of their design specifications. This wasn't occasional stress during hard driving, this was constant stress during normal driving. Oldsmobile's durability engineers documented the issue in internal testing. U-joint failure rates were running 30% higher on Stage 1 equipped cars compared to standard 455 engines. The drive shafts themselves showed signs of twist deformation after repeated hard acceleration cycles. The engineering team recommended reinforced drive shaft assemblies as standard equipment, but cost constraints meant these upgrades were only available as dealer-installed options. The real concern was cumulative fatigue. Metal components don't just break from a single overload event. They fail from thousands of cycles of high stress that gradually weaken the material structure. The Stage 1's flat, massive torque curve meant that every acceleration event was a high-stress cycle. Engineers calculated that drivetrain components in Stage 1 cars would accumulate fatigue damage at roughly double the rate of standard vehicles. According to internal Oldsmobile documentation, the powertrain division requested that Stage 1 engines be restricted to vehicles with mandatory heavy-duty drivetrain packages. That recommendation was overruled by product planning, who argued that such restrictions would limit sales appeal. The compromise was to include reinforced components in the factory installation, but not require them for customer orders. One engineering memo from Oldsmobile's reliability group stated plainly, "The Stage 1 torque output represents the practical limit of our current drivetrain architecture. Further increases would require complete system redesign." That wasn't marketing language. That was engineers acknowledging they'd reached a boundary. The Stage 1 also created challenges for the automatic transmission calibration team. The turbo-hydromatic 400 transmission used in most Stage 1 applications required custom clutch pack materials and modified shift programming to handle the torque without excessive slip or harsh engagement. Even with these modifications, transmission operating temperatures ran 15 to 20 degrees Fahrenheit higher than standard applications. Higher operating temperatures meant accelerated fluid degradation and increased wear on friction materials. Oldsmobile specified shorter transmission service intervals for Stage 1 cars, every 25,000 miles instead of the standard 50,000, but most owners didn't follow these requirements. Predictably, warranty claims for transmission issues ran significantly higher on Stage 1 vehicles. The irony was that Oldsmobile had built an engine that was almost too successful at its design objective. The goal was to create massive low-end torque for street performance. They achieved that goal so completely that it exposed limitations in every other component of the powertrain. The Stage 1 wasn't scary because it was unreliable. It was scary because it revealed how close to their limits the surrounding components were operating. Buick's approach to the 455 cubic inch displacement was even more aggressive than Oldsmobile's. The Buick 455 Stage 1 produced 510 pound-feet of torque at 2,800 RPM, the highest torque figure of any production engine available in 1970. Peak horsepower was listed at 360, but that number was almost irrelevant. This engine was engineered specifically for low-end force. The technical challenge facing Buick's engineers was unique among GM divisions. The Buick GS, where most Stage 1 engines were installed, used unit body construction rather than traditional body-on-frame architecture. This made the cars lighter and more responsive, but it also meant the chassis itself had to absorb and distribute the drivetrain forces rather than passing them through a separate frame structure. During validation testing, Buick's structural engineers discovered something concerning. Hard launches from standing starts were creating stress concentrations at the rear suspension mounting points that exceeded the original design calculations. The unit body structure was flexing more than anticipated, and that flex was causing localized stress that could lead to metal fatigue and eventual cracking. The problem wasn't immediate catastrophic failure, it was long-term durability degradation. After repeated hard acceleration events, inspection revealed micro-cracking at suspension mount locations. Left unchecked, these cracks could propagate over time, potentially leading to suspension component failure or body structure damage. Buick's solution was to implement reinforcement plates at critical mounting points and upgrade suspension bushings to stiffer compounds that would reduce movement and thus reduce stress cycling. But here's where it gets interesting from an engineering perspective. These modifications were implemented as a running change partway through the 1970 model year. Early production Stage 1 cars didn't have the reinforcements. Later production cars did. This created a situation where identical appearing vehicles had different structural capabilities. Buick's technical service bulletins noted the change, but didn't recommend retrofitting earlier cars unless they showed signs of stress damage. The engineering judgment was that the reinforcements improved margin but weren't absolutely necessary for normal use, a fine line that made some engineers uncomfortable. The Stage 1 also presented cooling system challenges. The engine's high compression ratio, 10.5:1, and aggressive cam timing created substantial heat generation. Buick specified a heavy-duty radiator and clutch fan setup, but even these struggled to maintain optimal temperatures during sustained high-load operation in warm climates. Temperature monitoring during durability testing showed that coolant temperatures could reach 220 degrees Fahrenheit during extended wide-open throttle runs, well above the ideal operating range of 180 to 200 degrees. At these elevated temperatures, several things happen. Coolant begins to break down chemically, reducing its effectiveness. Gasket materials soften, increasing the risk of sealing failures, and oil temperatures rise, reducing lubrication effectiveness. Buick's engineers understood that most customers wouldn't subject their cars to extended wide-open throttle operation, but the concern was that the engine didn't have much thermal margin for abnormal conditions. A partially restricted radiator, a worn water pump, or operation in extreme ambient temperatures could push the cooling system past its limits relatively easily. One technical report from Buick's powertrain division noted that the Stage 1 represented the maximum torque output achievable with current chassis and cooling system architecture without comprehensive redesign. That phrasing, without comprehensive redesign, was significant. It meant the engineers recognized they'd hit a ceiling, and going further would require fundamental changes rather than incremental improvements. The Stage 1's combination of extreme torque and unit body installation created a systems integration challenge that made Buick's engineering team genuinely concerned about long-term durability. They'd built an engine that was technically sound in isolation, but pushed the surrounding system, structure, cooling, drivetrain, into operating regimes that hadn't been fully validated for extended use. Pontiac's Super Duty engines represented a fundamentally different engineering philosophy than mainstream performance engines. These were purpose-built racing engines modified minimally to meet street legal requirements, rather than street engines modified for performance. That distinction created multiple technical challenges that made Pontiac's engineers nervous about long-term reliability. The 428 Super Duty used lightweight components throughout its construction. Thinner cylinder walls saved weight but reduced thermal mass and structural rigidity. Aluminum exhaust manifolds reduced weight and improved exhaust flow but introduced thermal expansion issues that cast iron didn't have. The reciprocating assembly used lighter weight components that reduced rotational inertia but provided smaller safety margins against mechanical failure. The aluminum exhaust manifolds became a particular point of concern. Aluminum expands at approximately twice the rate of cast iron when heated. During operation, the manifolds would expand significantly while the cast iron cylinder heads expanded less. This differential expansion created stress at the mounting points where dissimilar materials were bolted together. Pontiac's durability engineers documented stress cracking in the aluminum manifolds during thermal cycling tests. The cracks typically initiated near the mounting bolt holes, exactly where stress concentration theory predicted they would. The engineering team tried several solutions, different bolt torque specifications, various gasket materials, even experimenting with different aluminum alloys. Nothing completely eliminated the cracking tendency. The decision to proceed with production despite this known issue reveals the engineering calculation being made. The manifolds would likely last through the warranty period under normal use. They provided significant performance benefits in terms of weight and flow, and they could be replaced if they did crack. But it was a conscious choice to accept a component with known durability limitations because the performance benefits were deemed worth the risk. The thinner cylinder walls created different concerns. Less metal meant less heat capacity and less structural rigidity. During combustion, cylinder pressures push outward on the walls. Thicker walls resist this pressure with less deformation. Thinner walls flex slightly, which over many cycles can lead to bore distortion and increased piston-to-wall clearances. Pontiac's specifications for the Super Duty reflected these concerns. The engine required more frequent oil changes than standard engines, every 3,000 miles instead of 6,000. The specified oil weight was heavier to maintain adequate lubrication as clearances increased with wear. And the technical service bulletins explicitly warned against extended idle operation or continuous low-speed driving, which would heat-soak the engine without adequate airflow for cooling. These weren't normal requirements for a street engine. They were requirements that made sense for a racing engine, frequently inspected, carefully maintained, operated in controlled conditions. Applying them to customer vehicles meant Pontiac was asking owners to treat their street cars like race cars, which most wouldn't do. The Super Duty's solid lifter valve train required valve lash adjustment every 5,000 miles. This wasn't a suggestion. Incorrect valve lash could lead to valve-to-piston contact or inadequate valve seating, either of which could cause catastrophic failure. But valve lash adjustment required mechanical knowledge and specific tools. Most dealers could perform it, but most owners wouldn't bring the car in for service that frequently. According to Pontiac's warranty data, Super Duty engines showed higher than average failure rates after 30,000 miles, right around the point where deferred maintenance and accumulated wear would start causing problems. The engines weren't inherently unreliable, but they had no tolerance for neglect. One engineering report from Pontiac's performance division stated, "The Super Duty engines represent the minimum mass and maximum output achievable with current materials and manufacturing processes. Further optimization would require exotic materials unsuitable for production economics." This was engineers acknowledging they'd pushed conventional materials to their practical limits. If you're enjoying this deep dive into the engineering that terrified Detroit, hit that subscribe button. We've got 3 more engines coming, including the number 1 that even its own creator admitted probably shouldn't have been built. The LS7 represents perhaps the most extreme example of an engine that engineers knew was problematic before the first production unit was built. Internal Chevrolet documentation tells a remarkable story of engineering capability colliding with systems integration reality. The basic specifications seemed achievable: 454 cubic inches, 11.25 to 1 compression ratio, solid lifter camshaft with aggressive duration, and lift. Chevrolet's engine designers had built higher compression engines before. They understood the metallurgy, the combustion dynamics, the thermal management requirements. The LS7 wasn't pushing theoretical boundaries. Every individual component was within established limits. The problem emerged when engineers analyzed what happened when all that capability was actually used. The LS7 produced 512 pound-feet of torque at 3,400 RPM. That represented a 120% torque increase over the base 454 engine, but the transmission, drive shaft, differential, and axle shafts were the same components used across the entire 454 engine family. Chevrolet's transmission engineering group ran the stress calculations and delivered an uncomfortable assessment. The turbo-hydromatic 400 automatic transmission, even in heavy-duty form, experienced clutch pack loading that exceeded the design specifications when subjected to the LS7's torque output during hard acceleration. The shock loads during gear changes were high enough that long-term durability couldn't be guaranteed. The solution was to restrict the LS7 to manual transmission applications only. But even the heavy-duty M22 Rock Crusher 4-speed wasn't originally designed for torque levels this high. The gears were manufactured from stronger steel alloys and machined to tighter tolerances specifically to handle the loads. But even this wasn't a complete solution. Testing revealed that the drive shaft, when subjected to the instantaneous torque spike from a hard clutch engagement, could twist beyond its elastic limit. This didn't mean immediate failure, but it meant plastic deformation, permanent twisting that would accumulate over repeated events. Eventually, the drive shaft could fail from accumulated fatigue. Chevrolet's recommendation was to require heavy-duty drive shafts with larger diameter tubes and thicker walls. But this wasn't standard equipment. It was an option. An internal memo from Chevrolet's Reliability Engineering Group expressed concern that customers might order the LS7 without the necessary supporting hardware, creating liability exposure. The thermal challenges were equally significant. The LS7's compression ratio, combined with its cam timing and airflow capability, created combustion chamber temperatures at the upper limits of what the cooling system could manage. Chevrolet specified a 4-core radiator, heavy-duty water pump, and specific thermostat temperature, but these were still marginal for sustained high-load operation. Dynamometer testing showed that continuous wide-open throttle operation for more than 60 seconds pushed coolant temperatures above 220 degrees Fahrenheit. At those temperatures, the risk of detonation increased dramatically, even with premium fuel. And detonation could destroy pistons in seconds, not minutes. The fuel requirement was another source of engineering anxiety. The LS7 required minimum 100-octane fuel by the research method. This was premium fuel, but it had to be actual premium fuel, not mislabeled regular or mid-grade. Fuel quality varied significantly by region and even by individual gas stations. Running lower octane fuel didn't just reduce power, it invited detonation that could cause catastrophic failure. Chevrolet's owner's manual included explicit warnings about fuel requirements, but the engineering team knew many customers wouldn't read or follow these instructions. Internal estimates suggested that up to 40% of LS7 engines would experience some degree of detonation-related damage during their service life due to inadequate fuel octane. The solid lifter valve train presented maintenance challenges. Valve lash required adjustment every 5,000 miles to maintain proper clearances. Too tight, and valve float at high RPM could cause valve-to-piston contact. Too loose, and valve seating would be compromised, leading to burned valves and loss of compression. A technical report from Chevrolet's powertrain division laid out the situation clearly. The LS7 represents maximum performance output from the 454 platform, all supporting systems, cooling, lubrication, drivetrain, operate at or near design limits. Any degradation in component condition or fuel quality will result in reduced durability margin. Chevrolet produced the LS7 for exactly one model year, 1970. Production numbers were small, probably fewer than 200 units. The official reason for discontinuation was emissions regulations and changing market conditions. But internal documents suggest engineering concerns about warranty exposure and reliability issues played a significant role. One Chevrolet engineer speaking years later put it bluntly, "The LS7 was an engine we could build, but probably shouldn't have. We knew the margins were too tight. We knew customers wouldn't maintain it properly. We built it anyway because the competition was doing the same thing. Ford's boss, 429, represents one of the most technically sophisticated engines on this list, and paradoxically, one of the most problematic from a systems integration standpoint. The engine was designed specifically to meet NASCAR homologation requirements, which meant it needed to exist in production form, but wasn't really optimized for street use. The hemispherical combustion chamber design provided exceptional breathing capability. The canted valve arrangement allowed large valve diameters and direct intake and exhaust flow paths. From a purely thermodynamic perspective, the Boss 429 was brilliant. It could flow massive amounts of air and fuel, creating the potential for extraordinary power output. But that potential created problems throughout the rest of the engine systems. The first concern was oiling. The Boss 429 used a standard Ford 429 oil pump and pan design, which was adequate for a street engine operating at moderate RPM, but marginal for a high-output engine that could sustain 6,000 RPM or higher. During durability testing at sustained high RPM, oil pressure would drop below the minimum specification of 40 psi. This happened because the oil pump couldn't maintain adequate flow at the volumes required, and because oil starvation at the pickup occurred during hard acceleration or cornering when oil would shift in the pan away from the pickup tube. Ford's engineers tried multiple solutions. They modified the oil pump to increase flow rate. They added baffles and windage trays to the oil pan to keep oil near the pickup. They even experimented with dry sump oiling systems, though these never reached production. Nothing completely solved the problem within the constraints of production feasibility and cost. The solution Ford ultimately implemented was conservative engine calibration. The camshaft profile was deliberately mild for an engine with this much capability. The valve springs were specified to limit maximum RPM to around 6,000. The flywheel was heavy, which reduced acceleration but also reduced the shock loads on the bottom end during RPM changes. This was Ford deliberately limiting the engine's performance to keep it within the reliability envelope. Internal Ford documents show the Boss 429 was capable of making 650 horsepower with appropriate camshaft and carburetor modifications. In production trim, it was rated at 375 horsepower, less than some smaller displacement Ford engines. The difference was the margin between capability and durability. The valve train presented its own set of challenges. The hemispherical head design required canted valves, which created significant side-loading forces on the valve stems during operation. This is the same issue Chrysler dealt with in the 426 Hemi, but Ford's approach was different. Ford used shorter valve stems to reduce the lever arm length and thus reduce the side-loading force. This worked from a stress perspective, but created another problem: reduced valve-to-spring clearance. When valve springs can't control valve motion precisely, a condition called valve float that occurs at high RPM. There's increased risk of the valve contacting the piston. The conservative cam profile was partly designed to keep RPM below the point where valve float became a significant risk. But this meant the engine never achieved its theoretical power potential. Ford had built an engine capable of dominating NASCAR racing, then deliberately prevented it from doing so to ensure street reliability. A memo from the Boss 429 development team noted, "We have created an engine with 700 horsepower potential that we must limit to 375 horsepower production output to ensure component life expectancy meets warranty requirements." This represents a fundamental mismatch between design capability and application requirement. The Boss 429's physical dimensions created additional problems. The hemispherical heads were so wide that the engine barely fit in the Mustang engine bay. Carcraft, the specialty shop that installed Boss 429s into Mustangs, had to modify the Zeig, shock towers, and front suspension mounting points to create clearance. This wasn't simple bolt-in installation, it was structural modification. Each Boss 429 Mustang took approximately 1 week to complete at Carcraft and cost Ford significantly more than the retail price. Ford's internal accounting showed they lost between $800 and $1,200 on every Boss 429 sold. The business case depended entirely on NASCAR homologation benefits, race wins that would boost brand image and sales of regular production vehicles. When NASCAR immediately restricted the Boss 429 with weight penalties and intake limitations before it ever competed, the business justification evaporated. Ford had built an expensive, complex, technically sophisticated engine that couldn't achieve its racing objective and was overbuilt for street use. One Ford engineer involved in the Boss 429 program summarized it years later. "We built a race engine that had to be sold as a street engine, and we neutered it to make that possible. It was simultaneously the most advanced engine Ford had ever produced and a compromise from the beginning." The Boss 429 lasted exactly 2 model years, 1969 and 1970, with production totaling fewer than 1,400 units. The LS6 454 represents a more successful engineering balance than its more extreme sibling, the LS7, but it still pushed boundaries that made Chevrolet's engineers genuinely concerned about real-world reliability. With a 10.25-to-1 compression ratio, the LS6 sat just below the threshold, where detonation becomes a constant threat with period pump gas. But just below is still uncomfortably close when you're talking about forces that can destroy an engine in seconds. Chevrolet's combustion engineers had done the calculations, run the tests, and validated that the LS6 could survive on premium fuel with adequate octane. The concern was whether premium fuel with adequate octane would always be available. Fuel quality in 1970 was inconsistent. Octane ratings varied by region, by season, even by individual gas station. The advertised octane number at the pump didn't always match the actual octane in the fuel. Chevrolet specified that the LS6 required minimum 98 octane by research method, which translated to approximately 93 octane by the new anti-knock index. The engineering concern was straightforward. What happens when a customer fills the tank with inadequate fuel and doesn't recognize the detonation that follows? Light detonation causes minor efficiency loss. Severe detonation causes piston failure. Small particles of piston crown material break off, fall into the cylinder, and get crushed between piston and head on the next compression stroke. The damage escalates rapidly from there. The LS6 had no knock sensor, no electronic controls, no automatic timing retard to protect against detonation. It relied entirely on the driver recognizing the sound of detonation, a metallic pinging noise under load, and either backing off the throttle or switching to higher octane fuel. Many drivers wouldn't recognize detonation or wouldn't understand its significance. Chevrolet's internal projections estimated that between 25 and 35% of LS6 engines would experience some degree of detonation-related damage within the first 50,000 miles. Not all would be catastrophic failures, but all represented durability degradation caused by operation outside design parameters. The LS6's solid lifter valve train required valve lash adjustment every 5,000 miles. Incorrect valve lash could lead to several problems. Insufficient clearance could cause valve-to-piston contact at high RPM. Excessive clearance could cause valve seating issues and burned valves. The adjustment procedure required mechanical knowledge, specific feeler gauges, and approximately 2 hours of careful work. In practice, many LS6 owners either didn't know about the requirement or chose to ignore it, leading to predictable problems. Chevrolet's cooling system for the LS6 was more robust than the LS7, but still operated closer to thermal limits than engineers preferred. The 4-core radiator and heavy-duty water pump could maintain acceptable temperatures under most conditions, but sustained wide-open throttle operation in warm, ambient temperatures pushed coolant temps toward the 220-degree range. At elevated temperatures, several degradation mechanisms accelerate. Coolant begins to lose effectiveness through chemical breakdown. Gasket materials soften, potentially compromising sealing. Oil temperature rises, reducing lubrication effectiveness. And most critically, the margin to detonation decreases as intake charge temperature increases. Dynamometer testing showed that the LS6 could sustain wide-open throttle for approximately 2 minutes before coolant temperature climbed to concerning levels. This was adequate for drag racing. Quarter-mile runs took under 15 seconds, but inadequate for road racing or extended high-speed driving. According to Chevrolet's warranty database, LS6 engines showed failure rates approximately 60% higher than standard 454 engines. The failures weren't random. They clustered around predictable modes: detonation-related piston damage, burned valves from incorrect valve lash, overheating-related head gasket failures. Each represented a case where real-world operation diverged from engineering assumptions. One technical summary from Chevrolet's Reliability Engineering Group stated, "The LS6 represents near-optimal performance from the 454 platform within production cost constraints. Reliability is acceptable when operated within specified parameters. Durability degradation occurs when parameters are exceeded, which field data suggests occurs in approximately 30% of customer applications." That 30% figure, nearly one-third of LS6 engines experiencing some form of parameter exceedance, represented the gap between engineering intent and customer reality. Chevrolet had built an excellent engine that required proper fuel, regular maintenance, and knowledgeable operation. In the real world, those requirements weren't consistently met. The LS6 continued through 1971, but with reduced compression ratio to 8.5 to 1 to meet tightening emission standards. Power dropped from 450 horsepower to 365. The 1970 LS6, with its 10.25 compression and tight operational margins, represented peak performance before regulations and reliability concerns forced compromise. The 426 Hemi enters this list not because it was the most powerful engine. Several competitors made comparable horsepower, but because it combined more distinct engineering challenges than any other production big block. The Hemi demanded more from its operators, required more careful maintenance, and had less tolerance for deviation from ideal conditions than any engine Detroit offered in 1970. Start with the valve train, because this is where the Hemi's fundamental design created permanent compromises. The hemispherical combustion chamber required canted valves positioned at angles from the cylinder axis. This valve arrangement demanded rocker arms positioned nearly horizontal, creating massive side-loading forces on the valve stems during operation. Every time a valve opens, the rocker arm pushes on the valve stem at an angle rather than straight down. This side-loading creates friction against the valve guide and causes accelerated wear on both the valve stem and guide surfaces. Chrysler used bronze valve guides and hardened valve stems to combat this wear, but they couldn't eliminate it. Durability testing showed that Hemi valve guides wore at rates 40 to 60% higher than wedge head engines. The wear wasn't catastrophic, but it was measurable and progressive. After 50,000 miles, valve stem to guide clearances in a Hemi would often exceed specification, leading to reduced sealing, oil consumption, and potential valve control issues at high RPM. Chrysler's service recommendation was to inspect valve guide wear every 25,000 miles and replace guides when clearances exceeded specification. This was more frequent maintenance than competing engines required and represented an operational cost that most customers didn't anticipate. The oiling system presented its own set of concerns. The Hemi's oil pump was located at the front of the engine, meaning oil had to travel the full length of the crankshaft to reach the rear main bearing, the most heavily loaded bearing in the engine. Under hard acceleration or cornering, oil in the pan would shift away from the pickup tube, potentially causing momentary starvation. Chrysler added windage trays and pan baffles to mitigate this issue, but the fundamental layout created vulnerability that couldn't be completely eliminated. During track testing, oil pressure would occasionally drop below specification during sustained cornering, particularly right-hand turns where centrifugal force moved oil away from the pickup on the left side of the pan. The concern wasn't that pressure would drop to zero, but that even temporary pressure reductions below 40 psi could lead to bearing damage over time. Bearings rely on a continuous oil film to prevent metal-to-metal contact. Any disruption in that film, even momentarily, causes localized wear that accumulates over many cycles. The combustion chamber design, while thermodynamically superior, created thermal stress challenges. The hemispherical shape meant heat distribution on the piston crown wasn't uniform. Certain areas, particularly the regions directly under the valves, experienced higher temperatures than others. This thermal gradient caused differential expansion across the piston crown surface. Chrysler used forged aluminum pistons with more robust crown designs to handle this stress, but thermal cycling still took its toll. Documented warranty claims included cracked piston crowns that showed fatigue patterns consistent with repeated thermal expansion and contraction. These weren't detonation failures. They were material fatigue from thousands of heating and cooling cycles creating stress at the microstructural level. The Hemi's fuel requirements were absolute, with compression ratios starting at 10.25 to 1 and reaching 10.5 in some variants. Premium fuel was mandatory. But the Hemi was even less tolerant of fuel octane deviation than the LS6. The combustion chamber shape created higher peak cylinder pressures, which increased detonation sensitivity. Running inadequate octane fuel in a Hemi didn't just reduce performance, it invited catastrophic failure. Piston crown failures from detonation were among the most common warranty claims. And unlike engines with more detonation margin, the Hemi could go from normal operation to severe detonation damage very quickly if subjected to heavy load with insufficient octane. The maintenance requirements extended beyond valve adjustments. The Hemi required specific high-zinc oil formulations to protect the flat tappet camshaft and heavy valve spring loads. It required strict adherence to warm-up procedures before heavy load operation. Cold oil couldn't flow adequately through the long oil passages, creating temporary starvation risk at startup. It required careful attention to ignition timing, which had to be set precisely to avoid both pre-ignition and reduced performance. These weren't unusual requirements for a high-performance engine, but they were more stringent and less forgiving than mainstream offerings. The Hemi demanded mechanical sympathy, an understanding of why these procedures mattered and what happened if they weren't followed. Chrysler's warranty data painted a clear picture. Hemi engines had failure rates approximately 80 to 90% higher than standard 440 wedge engines. The failures clustered around predictable modes: valve guide wear, detonation-related piston damage, oil starvation bearing damage, and maintenance-related issues like burned valves from incorrect adjustment. Internal Chrysler analysis showed that approximately 60% of Hemi failures were operator-related, inadequate maintenance, incorrect fuel, operation outside specifications. But even the design-related failures were higher than competing engines. Tom Hoover, the engineer who led Hemi development, was asked in a later interview why Chrysler built an engine with such demanding operational requirements. His answer revealed the thinking of the era. In 1966, we needed to win races to sell cars. The Hemi could win races. That it required expert maintenance and careful operation was secondary to its racing capability. By 1971, when we discontinued it, the market had changed. The Hemi's physical dimensions created serviceability issues that affected long-term ownership. The wide heads left minimal clearance in most engine bays. Changing spark plugs required removing multiple components first. Valve adjustments required specialized tools and access that was difficult in tight spaces. Even routine maintenance took longer on a Hemi than competing engines. Chrysler discontinued the street Hemi after the 1971 model year. The official reasons were emissions regulations and insurance industry pressure. The compression ratio had already been reduced to 8.8 to 1 for 1971, dropping power to 350 horsepower. But internal documents suggest reliability concerns and warranty costs also influenced the decision. A final engineering assessment from Chrysler's powertrain division stated, "The 426 Hemi represents peak naturally aspirated performance from conventional materials and manufacturing processes. Its operational requirements exceed typical customer capabilities. Its maintenance demands exceed typical customer willingness. Continuation cannot be justified on business merit regardless of technical achievement." That assessment explains why the Hemi scared its engineers. Not because it was a bad design, it was brilliant. But it required everything to be right: proper fuel, correct maintenance, knowledgeable operation, ideal conditions. In the real world, everything is rarely right, and when things weren't right with a Hemi, the consequences were expensive. These 7 engines, the Oldsmobile 455 Stage 1, Buick 455 Stage 1, Pontiac 428, Super Duty, Chevrolet LS7 454, Ford Boss 429, Chevrolet LS6 454, and Chrysler 426 Hemi represent the peak of American big block development. They also represent the point where engineers realized that technical capability and practical viability aren't the same thing. Each engine achieved remarkable power output through sophisticated engineering and careful optimization. Each also operated with margins so narrow that real-world conditions, imperfect fuel, deferred maintenance, aggressive driving, environmental factors could push them past their reliability limits relatively easily. The engineers who designed these engines weren't reckless or incompetent. They were brilliant professionals who understood exactly what they were building and what the limitations were. They documented their concerns in technical reports, recommended solutions in engineering memos, and implemented safeguards where possible. But they also worked within business realities that demanded maximum performance regardless of the long-term consequences. What made these engines scary wasn't that they failed frequently. Most didn't. What made them scary was that they succeeded so completely at their performance objectives that every other system, cooling, lubrication, drivetrain, chassis, was pushed to its limits trying to keep up. They revealed how close to failure thresholds conventional automotive components actually operated, and what happened when you exceeded those thresholds even slightly. Modern engine design has learned from these examples. Contemporary high-performance engines make more power than these big blocks ever did, but they do it with substantially larger safety margins. Electronic controls compensate for fuel quality variations. Improved materials handle higher stress loads. Better manufacturing tolerances reduce variability. The fundamental lesson that engines must survive real-world operation, not just idealized testing, has been thoroughly absorbed. These 7 engines remain legendary precisely because they operated at the edge. They represent a moment when American manufacturers prioritized performance over everything else and discovered where the actual limits were. The engineers who built them gave us technical knowledge that continues influencing design decisions 50 years later. If you've owned, maintained, or worked on any of these engines, share your experience in the comments. What surprised you about their requirements? What failures did you encounter? What made them worth the extra effort despite their demands? And if you want more deep dives into the engineering that defined the muscle car era, the successes, the failures, and the engines that pushed boundaries nobody thought possible, make sure you're subscribed. We've got more stories of American automotive ambition that went too far, and sometimes that's exactly what makes them unforgettable. Thanks for watching, and I'll see you in the next video.